Good morning, students. Today we'll start module 4 quantum mechanics. In that, introduction to quantum mechanics. So in quantum mechanics, one of the most important concept is black body radiation, and this can be understood by studying the color concept method. Color concept means in our daily life we see things around us varieties of colors. For example, if any material or any body, if it looks like blue means, so the body or a material which absorbs all the colors but it reflects blue. So as we know that electromagnetic spectrum, so the electromagnetic spectrum, the wavelength lies in 400 nanometer to 700 nanometer, and each of this wavelength that contributes one color like Vibgyor. The same thing, suppose if another example, if any body or material, if it looks like red means the material which is ability to absorb all the incident radiation but it reflects red color or red wavelength. And the same thing, if the material it looks like white means the body or material which is ability to absorb all the incident radiation, hence, and also it reflects all the colors or all the wavelength. That's why it looks like white. And similarly, if material or a body, if it is looks like black means the material which is ability to absorb all the radiation or colors, but since there is no light is reflect or transmit, and such a body is referred as black body. In general, the definition of black body, it says that a material or a body which is ability to absorb all the incident radiation of electromagnetic waves, since there is no light is reflect or transmit, and such a body is referred as black body. And at thermal equilibrium, if the body starts heating, if we go on increasing the temperature of black body, then the radiation, whatever the radiation it has absorbed, that radiation is going to emit, and that emitted radiation is called as black body radiation. In 1859, Kirchhoff formulated first practical body, and he carried out several experiments and studied energy distribution curve with respect to temperature. Now we can see the energy distribution in black body radiation with respect to temperature curve. So there are points like A, B, C, D, so which represents the lambda max or the peak wavelength with respect to particular temperature. In y-axis there is a energy, and in x-axis there is a wavelength. So energy as a function of wavelength with respect to temperature. So from this curve we can note down the points like, if as temperature increases the energy density curve is also increases. The first point is, as temperature increases the energy is also increases. And also we have noticed that like point A, B, C, D, so this is shifted towards the lower wavelength side. Like as temperature increases the point is shifted, means the peak wavelength or lambda max wavelength is shifted towards the lower wavelength side. And another aspect is, as temperature increases the full width half maxima or peak wavelength or peak, that is becomes narrower. Initially at 300 Kelvin it covers entire wavelength, like UV lower wavelength is ultraviolet, visible and infrared. But at 3000 temperature the curve is slightly, it is hump, and it covers only certain wavelength like visible and IR. If we go on increasing the temperature, finally the peak wavelength A, that indicates lambda max with respect to temperature about 6000 Kelvin. So here it covers only certain wavelength, that is visible range. Later, William Wien and Lord Rayleigh and Jines carried out theoretical investigation on black body, and they derived equation for black body. It's just like an expression. For example, in a straight line we are giving expression, theoretical expression is y is equal to mx plus c. The same thing in black body curve is also they tried to give a theoretical expression. So first thing is Wien's law. In 1896, Wien found the relation between wavelength of emission of black body and temperature is given by the expression E lambda into D lambda, which is equal to C1 into lambda raised to minus 5 into exponential of minus of C2 divided by lambda into T into d lambda. In that, lambda is wavelength, it's a variable function, and C1 and C2 are the constant value, and T is the absolute temperature. And this law holds good only for the shorter wavelength side, because if lambda tends to 0, the E becomes 0, so total energy becomes 0. But it fails to explain the longer wavelength side. If you go on substituting the value of lambda, which is equal to infinity, it gives the infinite value, but as per the practical demonstration, it is not possible. Hence, this theory fails to explain the longer wavelength side. And the second scientist, Rayleigh and Jaynes, they have formulated one equation, that is E lambda into d lambda, which is equal to 85 kT divided by lambda raised to 4 into d lambda. So the product of kT, that is nothing but it is the Boltzmann constant into absolute temperature, and lambda is the wavelength. Again, this law also holds good only for the longer wavelength side, but it fails to explain shorter wavelength side. For example, if we substitute lambda, which is equal to 0, so E becomes infinite. It means at 0 wavelength the infinite energy is going to transfer, but it is not possible in practical cases. Hence, this theory again fails. So both laws are failed to explain entire wavelength of black body spectrum. So initially the Wiens explained only for the shorter wavelength, and Rayleigh-Jeans explained only for the longer wavelength side. And later in 1900, the Max Planck has derived a black body spectrum by taking the following assumptions. So the first assumptions are: energy is absorbed or emitted by a black body, it is directly proportional to its frequency. So energy absorbed or emitted by a black body, it is directly proportional to its frequency, and it is given by E, which is equal to h mu, because E is directly proportional to mu or frequency, or which is equal to some proportionality constant, that is h into mu, where h is nothing but it is the Planck's constant. And also it is observed that energies are not in the continuous form, it has a discrete units, and it has integral multiple of its frequency, or E, which is equal to nh mu. By taking these two assumptions, he has derived one equation, that is E lambda into d lambda, which is equal to 85 hc divided by lambda raised to 5 into 1 over E raised to h mu by kt minus 1 into d lambda. In that, h is Planck's constant, c is speed of light, and lambda is wavelength, and again kt, the product of kt is Boltzmann constant into absolute temperature. And this law, which holds good for entire wavelength, like shorter wavelength and longer wavelength, or entire spectrum.